Okay, welcome to this next video covering further details on bonding, moving from molecular systems to metal systems and then into intermolecular forces where we're looking at forces between molecules. So far we've covered ionic bonding. We saw that they were very strong and they involved discrete charges on ions that resulted from a charge transfer to generate those ions, and that these ions can pack with various coordination numbers to extend the ionic bonding into 3 dimensions. We'll look today at covalent bonds and then touch on metallic bonds, which aren't shown on this diagram, but they're largely very strong as well. So metallic bonds are in this region here, and that completes our understanding here for within molecules, within the material, those forces. And then any that exist between molecules are intermolecular. And so here we'll see things like ion dipole, hydrogen bonding, dipole, and then London dispersion, or as your textbook refers to it, dipole-induced bonds. Okay, so previously, like we mentioned, we saw ionic bonds. They were a primary chemical bond involving ions that resulted from electron transfer between atoms, and that those ions were attracted to one another by Coulombic force, and that the estimate of the ionic radii could speak to the ultimate ionic bond. In covalent bonds, we have to remember that here we're dealing with nonmetals bond to nonmetals usually, and so the result there is that we end up with sharing of electrons between atoms. So we previously saw this with hydrogen with 1 electron coming together with hydrogen with 1 electron, and these two would establish a hydrogen 2 electron bond, where the 2 electrons here are in the vicinity of this hydrogen, so that hydrogen looks like a helium atom in its electronic configuration, and that hydrogen there also looks like a helium atom in its electronic configuration. Okay. Let's clean some of this up here. In more complex systems, it can be a little bit more constructive to consider a planetary model again for the atom, and so we'll show that here. And in this case, 2 chlorine atoms are shown, so Cl, Cl, each with a valence shell, so their outermost shell having 1, 2, 3, 4, 5, 6, 7 electrons. And so by temporarily sharing electrons between the two, we can satisfy a need for the outer valence shell of each atom to look like the next largest noble gas, where we now put an electron from a neighboring chlorine atom within that vicinity of the bonded chlorine. Okay, so this is the basis for sharing electrons in the Cl2 chlorine gas molecule. So in short, that maximizes the population of the outer orbital, so it satisfies the octet rule, if you will, and puts 8 electrons in the outer orbital, provided that we can consider sharing of one of the electrons from a neighboring chlorine atom. Okay. Good. So just to elaborate a little further, so a lot of the details of our drawings have implied certain things about the electron count. So as we've seen before, the valence shell of a chlorine atom has 7 electrons because chlorine is in the 7th column in the periodic table. And so we can see here that these 7 could be arbitrarily assigned to the rightmost chlorine, and then these 7 here could be attributed to the leftmost chlorine, and that would indicate that the 2 in the middle here are the shared electrons for the chlorine bond. Okay, so we see that each dot represents those electrons from the valence shell, and those 2 that are on the axis between the 2 are those that are shared, and those make up the 2 electron bond. Okay, so we'll see this type of notation for indicating a covalent shared bond throughout organic molecules and polymer materials in this course. So the line represents the bond and its directionality, so notice that it's indicating that there's an axis directly between those 2 chlorine atoms in this example. And this is quite different than the ionic bonds that we saw, which were more non-directional. We simply brought hard spheres close together per a hard sphere packing model and tried to maximize coordination numbers while respecting radius information about filling space in those ionic materials. Okay, and as mentioned, the single line represents a single pair of electrons that are shared. Okay, so here's an example of the polyethylene molecule. And so at first glance, it looks quite complex, but if you take a moment to sort of examine all the dashes and the directionality of any covalent bonds that exist, you'll see that there is a main chain of covalent linkages tethering all the carbons together in this material. And coming off that main chain are bonds to adjacent hydrogens all the way across. So these are all the primary covalent bonds that exist in polyethylene as we have it. These are what we call the intramolecular bonds. So these bonds establish the conductivity of the molecule itself. And there are further bonds between segments of this long molecule or between other molecules that are the intermolecular forces that we'll touch on towards the end of this video. Okay, so we'll contrast that scenario just once more visually here by looking at the ionic compound that is in silica or found in glass and quartz. So this would be a tetrahedron of oxygen atoms with oxygen at each of the corners and a central silicon having a 4+ state in its cationic form, and each of the oxygens having a 2- state. Okay, so clearly we're not electroneutral, and so there would be a driving force to extend bonding further into 3 dimensions and continue the pattern of this tetrahedron throughout the bulk of this silica or glass. Okay, so we see here that this central silicon atom has ionic bonds to each of the adjacent oxygen atoms in this case. Quite a bit different than the conductivity of the covalent compound that was polyethylene that we saw in the previous slide. Just like we had in our lessons on ionic bonds, these covalent bonds have a very similar binding energy curve. Okay, so recall this is our energy scale, and at a minimum in this curve, we know that is as far as the x coordinate here represents the bond length, the average bond length for the covalent bond, and the vertical distance from that minimum up to the x-axis is an energy amount, and so that energy would be the dissociation energy of the particular covalent bond described by this graph. So this value would allow us to understand how much energy it would take to break that bond, and bond dissociation energies are often tabulated to help us understand the bond strength or the bond energy here. Earlier in a video we mentioned that single bonds are longer and weaker than double bonds, which are a little shorter and a little stronger, and even shorter and stronger still is the triple bond. And so we might expect the bond length to adjust as we go from single to triple from single to double to triple bonds. So we might move the x coordinate of the well to the left, and if the bond energy is going to increase as well, the well would get a little deeper. So we might expect a double bond curve to look something like this, and a single bond curve, or a triple bond curve, apologies, to be deeper and further towards the y-axis here. So this would be the triple bond, and that black one there is the double bond. And that could be the original here is the single bond. Okay, often in carbon-based materials, if there's sp3 hybridization and 4-fold single bonding at a carbon, we often see 109.5 degrees, an angle associated with a tetrahedral arrangement of electron groups or bonded atoms at that carbon. And so this is indicating that an atom over here at this corner of the cube, one over here, and one in the back here are the 4 bonded materials. So this could describe the diamond lattice, carbon single bonds in three dimensions throughout, with a central tetrahedron establishing the repeating pattern to that 3-dimensional lattice. The 4-fold bonding is also often found in polymeric materials, as we saw in polyethylene. 2 of those bonds were reserved for hydrogens, and 2 of those bonds were reserved for the conductivity of the main polymer chain. And you see the same structure in other semiconductors like silicon and some ceramics as well. Okay, and so hopefully it goes without saying to you that the bond angle is as we see in this diagram, is what's described between 3 atom centers. Like any other angle, three features need to be identified to describe a bond angle, and in this case that bond angle was 109.5. Okay, so here we have some tabulated bond energy data. So this might be determined from a dissociation energy experiment, where energy is applied to bonds to break them. So in other words, to climb up the well in our earlier graph. Okay, so the bond energy here. We see that tabulated in 2 sets of units in kilocalories and kilojoules per mole of those bonds. Okay, so notice that we're considering many of those bonds per mole of those bonds. And we mentioned earlier that as we consider single to double to triple bonds, we would expect a deeper well. And so that would register as more energy to break 1 mole of those bonds, so a higher kilojoule per mole value in the bond energy. And so we see that increasing here as we go down to carbon-carbon series. And accordingly, if we were correct in that the equilibrium bond length, as inferred by the x-coordinate of the well in this energy versus interatomic distance of the bonded atoms, that should also decrease. So we should make shorter bonds as we make multiple bond options. So carbon-carbon, carbon-double bonds, and carbon-carbon triple bonds get shorter as we consider the multiple bonding options. You can see similar kind of trends per other sort of arguments, things like how good the overlap is for the sharing of the electrons between centers. So when you have very different sized atoms, you can have very poor bonding. So for example, oxygen and silicon are in different rows in the periodic table, and so the orbital overlap to establish a 2 electron shared bond here is a little less than ideal, because the silicon atom is so much larger given its depth in the periodic table. When we have a more matched pair, like in the twin, that is the oxygen-oxygen, we have other reactivities here to consider. So here's the peroxide type unit here, which you may understand to be a little bit reactive. Considering OH as an example here of a heteroatomic, 2 different atoms, to compare to the oxygen-silicon, you can see that the overlap between orbitals for sharing is more favorable, and we establish stronger bonding. Okay, so as you may have seen from other courses, and just as another reminder, electronegativity, this is the ability of a bonded atom to attract an electron to itself in that circumstance. Generally, all the electronegativity values are imposed here on top of the periodic table, and so you can see here that some of the lowest electronegativity values are in this corner of the periodic table, and some of the highest electronegativity values are up in that corner of the periodic table. And in general, the electronegativity values increase as we go from the bottom left-hand corner to the top right-hand corner of the periodic table. We'll note here that the transition metals here, which establish their own unique set of elements and have to be described by metallic bonding, are largely low electronegativity elements, and so this establishes the metallic bonding circumstance that we'll touch on in a moment. Okay, so in metallic bonding, the model here is that adjacent atoms share electrons in a non-directional way as a consequence of their modest electronegativity values. This is in contrast to what we saw in ionic bonds, where we have non-directional bonds and electron sharing complete from one atom to the next. So perhaps transfer is an even stronger word to use here, where that electrons transfer to give the charges that are discrete on the ions that are formed here in the cation and in the anion. Covalent, on the other hand, we have electron sharing between adjacent atoms without complete transfer of the electron, and more directional bonding is established as a result of this. So in sum, we have non-directional sharing in the metallic bond as we do in the ionic bonds. We have complete electron transfer in ionic to make our ions, and we have more shared electrons in the directional covalent bonds, and a vast sort of distributed electron throughout the material in the metallic bond. Okay, so metallic bonding, as we mentioned here, is non-directional electron sharing, quite a bit different than covalent bonding. So how do we describe that? So shown here are the metal centers. So these are the atoms with their core electrons shown in sort of the white, and the valence electrons, which are held loosely because of the low electronegativity values of the metals, are shared uniformly throughout the material. So all valence electrons are distributed throughout all of the material, which is often referred to as a sea of valence electrons, which are all negative in charge, of course, and every atom center is therefore positive in its discrete kind of examination, and therefore would be bonded to that sea of electrons. So the valence sea of electrons shared throughout the lattice here is what holds all metal atoms together. So hopefully that picture of a sea of valence electrons helps you understand the non-directional electron sharing that exists in metals. Okay, so as a consequence of this, we understand, and you've likely come to know, that metals are very electrically conductive and even thermally conductive. And this has to do with how easy it is to apply electrical current or electrons into the material and out of the material as a consequence of the ability of electrons to roam freely throughout the metal. So that explains the high electrical conductivity that we see for metals. Same thing goes for thermal conductivity. We can transmit heat throughout the material very easily, since atoms are going to be allowed to vibrate and establish that temperature, that elevated temperature owing to the heating energy applied. The sea of electrons here is also easily excited by incoming radiation from the electromagnetic spectrum, or that is to say, it's easily excited by light, in fact. So photons of light can actually be absorbed by the sea of electrons, and this absorption of the light leads to the shiny color that is often seen with metals, and sometimes the opaqueness depending on the metal. We mentioned in the opening of this video that metallic bonding is quite strong. So here are some metals and their data for the heat of sublimation. So this is the energy it takes to transform the metal from its solid to its gas state. So here we would be taking 1 mole of metal atoms, and the kilojoule value for that is the amount of energy required to volatilize 1 mole of those solid metal atoms into their gas state. So here you can see that most of these kilojoule per mole values for the heat of sublimation of these metals are quite high. Some of these values are about as high as some of our ionic compounds that we've seen before, so hundreds of kilojoules per mole. When we compare directly between metals of the same type and their oxides, so here's iron and its iron oxide, and likewise with magnesium oxide, and titanium with titanium oxide, we can see that the kilojoule per mole values are a bit higher in the ionic compounds in their oxides rather than the metallics. So this is why metallic bonds are regarded as just a little less strong in bonding energy than that of the ionic compounds, like their oxides.